Hi, welcome to Live for Calculus. Today we're going to be exploring the first lecture in a series about multivariable calculus, and we're going to start off by discussing what is a vector. A vector is something that has a magnitude and a direction, um, or length. Uh, and you can kind of see that over here on my diagram. This would be a vector here, and it is represented by a harpoon. Know that you're working with something that can also be defined as components. Well, what does that mean? When I define something as components, it means I'm working as a parametric. Um, Parametrics are when I take things in terms of their variables. So right now in this plane that we have here, looking over here, um, in my plane, I have this line A, this vector A. Vector A can also be quantified by the length in the direction it goes this way, the length it goes this way, and how far it is from the origin this way. Why would that be useful? Because sometimes it's easier to write things as a parametric, there's that word again. Parametrics are denoted by these weird bracket things. And whenever you see something in that, it means that you're looking at it in terms of its components again. So really nail that home. Something you need to know when I see these brackets. Um, I'm talking about things defined by their components. But back to my drawing over here. Um, it would be so much easier if I could write this vector A like X, Y, and Z. When I write it in terms of X, Y, and Z, I can then find its length. So if I look over here, the length of A, which is noted by absolute value brackets around A, the vector A, gives me a scalar quantity. What is a scalar quantity? It's something that doesn't have variables in it. It's just a number. Um, so let's write that down. So in physics, I would say that velocity and acceleration are both vectors, but speed is a scalar quantity. Um, and then just to touch on that a little bit more, vectors such as velocity and acceleration both have magnitude and direction, whereas speed does not have a direction. Speed is simply a number. And that's why it's important to know the difference because I don't have negative speed. Um, I can have negative velocity and acceleration. Um, and now direction. The direction of vector A would be noted by writing dir of A in parentheses. And now we're gonna come back to this idea, but let's work on length of A. What can I do with length of A? Let's generalize. So generally speaking, I can write A as a vector in its parametric components. So for an example, it would be like if I was to see this in the real world, I could see 1, 2, 3, and that would mean that I have 1 unit in the X direction, 2 units in the Y direction, and 3 units in the Z direction. Let's see what's happening down here. So as we said earlier, this means the length of A. The length of A is really similar actually to like if you've seen it before and you're familiar with it from your Calculus 2 class in college or your Calc BC or AP class at the AP level, when I um, take a parametric equation and I square each of its components to then give me its length in like one variable. It's exactly identical to that. Or when I have things in x, y components and I wanna actually let's make this parametric. When I have things in x, y components and I want to make it one variable, so let's define this variable as z. If I want to get this in one variable, I simply take z and it would be equal to the square of x squared plus y squared. Now, this would look familiar to anybody who is familiar with statistics at the AP level, at the college level. You would have been familiarized with this in the Calc BC classes, Calc AB class, maybe even like an honors calculus course, really anything like that. And it's that same idea, and it really comes back even more basic to the Pythagorean theorem. So, I'm finding the length of the hypotenuse. So right now, if I was to call this x, this y, I'm really just finding z up here. And the same thing applies to three variables. And this really expands infinitely. Maybe let's call variable, not variable, vector c, um, C1, C2, C3, C4. If I wanted to find the length of C then, this would simply be written as uh, C1 squared plus C2 squared plus C3 squared plus C4 squared. And this theorem will go on infinitely. Um, all of this goes to say, under let's generalize, is that I can take my parametrics, I can square each component, and that'll give me its length, which again will be a scalar. Um, in comparison, this direction will be a vector. Just to make sure we're good on that, the direction will be a vector and the length will be a scalar. So now let's look at an example of length. So if I'm given my vector A is 6 units in my x direction, 2 units in my y direction, and 3 units in my z direction. You can see my very bad drawing here. Um, and I want to find the length of A. If I was to redraw this in a simpler way to see, so instead of looking at it from this weird angle, let's just redraw it to look like this. Oops. Um, this would be A. Now I have some units up and some units over. Um, if I want to find the length of A, I actually know what this is, don't I? Kind of. Let's figure it out. So, what I do have is that let's change my color too. This is 2 units over from the origin point of the graph, and it's 6 units up. What can I do with that? I can find this length because we know that this is 6 and this is 2. So I'm going to use the Pythagorean theorem first, and I'm going to say that 6 squared plus 2 squared equals, we'll call this, we'll just call it question, no, we'll call it Q squared. So I have 36 plus 4 would be 40 equals Q squared. So I'm gonna have 2 root 10 is equal to Q. And I don't have to put that into simplest form. It's not necessarily going to make my life any easier down the road. But now, what am I going to do with this? That's a great question. I'm going to come back over here and I'm going to say, wow, I now know that the length of this is 2 root 10. What do I do with that? Let's call this vector B. Specifically, this is the length of vector B. See here? Because this would be B's components. This and this would be B's components. Specifically, B would be vector B, which I can tell from this graph because I'm saying that it starts at my origin. Would be 6 to 0. And now I can take B and I can call B this B. So how does this help me now? Well, if I want to find the length of this, I have this component. This is 3 units. I can do the same thing I did to find the length of B, and I can use the Pythagorean theorem essentially to find the length of A then, which would give me the length of B squared plus 3 squared for my other component, which would equal, oops, square root this. 40 plus 9, and the length of A will be 7 units. Now, that's one way that I could do this. That would be more beneficial if I was missing some of this, if I had a missing variable, but to provide a well-rounded, how many different ways can I manipulate these vectors example, um, we did it this way. Uh, but I can prove myself by then just finding the regular old length of A, which will be defined by the square root of its components named up here. So it'd be 6 squared plus 2 squared plus 3 squared. So give me the square root of 49, which will equal 7 units. And that was a nice way to check ourselves. Um, let's do a summary and then try one of these problems on your own. So to summarize what we did, we learned that vector A consists of components I hat, j hat, and k hat. Now, to go back over this, in case I didn't explicitly mention, um, but you can see that I drew them on the graph up here. I hat, j cat, I hat, j hat, and k hat are unit vectors, which are useful on the x, y, and z axes um, to represent components of your vector. That's really all there is. I'm not going to try to over explain that. Um, so back down to summarize. Um, Parametric are defined by components. Notation, the length of A is show like written as the absolute value of A. Or I just call them in my head absolute value brackets. And the direction of A is denoted by the dir of A. Hopefully you have a good understanding of this. And now let's try another problem. So let's say given um uh A equals. So now go ahead and try this on your own. I will have a solution worked out and then I will walk you through it. Okay, so now let's check our answer. So for this problem, my answer that I got was 2 root 6 for my final. And I got this by saying that I know that I have this length and this length, which would give me this triangle over here. A triangle that's 2 units up and 4 units over. Um, Lengths. And then I can use the Pythagorean theorem to say that 2 squared plus 4 squared, and the square root of that would be equal to the length of B. And then once I have the length of B, I know that it makes up this B, makes up this triangle here, and this would be the length of B. So now I can use the Pythagorean theorem again to just represent that the length of A will then be represented by the length of B squared plus my known variable, um, my known length. Uh, that would be this height here, which would be 2. And this gets me my final answer of 2 root 6 or root 24. Um, so if you have any questions or issues with that, you can leave them in the comment section and I'll try to get back to you as soon as possible.